Picture this: a 300-ton metal monster, tall as a 5-story building, hanging suspended beneath a converted oil tanker in the middle of the Atlantic Ocean. Cables thick as a man's arm snake down into the black depths, carrying enough electrical power to light up a small city. And then the sound begins. The acoustic pulse that erupts from this underwater behemoth is so powerful it can be heard thousands of miles away. Marine life flees in terror. The ocean itself seems to scream. This is Project Artemis in action, the Pentagon's most ambitious and ultimately doomed attempt to turn the entire Atlantic Ocean into America's ear during the Cold War. Welcome to Never Built, where we explore the most spectacular technological failures in history. I'm your host, and today we're diving deep into one of the most expensive underwater disasters ever conceived by the United States military. What do you think? Was it pure ambition or a dance with destiny? Let me know in the comments. If you're fascinated by the stories of technologies that could have changed the world but never quite made it, make sure to subscribe and hit that notification bell. These are the tales they don't teach in engineering school. The year was 1961. President John F. Kennedy had just taken office, the Berlin Wall was rising, and beneath the waves of the world's oceans, a new kind of warfare was taking shape. Soviet submarines, sleek and silent, prowled the depths like mechanical sharks, carrying nuclear missiles that could obliterate American cities in minutes. The Pentagon was terrified. Traditional sonar systems of the era could barely detect these underwater phantoms until they were dangerously close. American naval commanders lay awake at night, haunted by the thought of Soviet ballistic missile submarines lurking just off the coast, invisible and undetectable. Admiral William Rayborn, head of the Navy's Special Projects Office, was a man obsessed with the impossible. He had already overseen the development of the Polaris submarine-launched ballistic missile system, turning American subs into underwater nuclear fortresses. But now, he faced the opposite problem. How do you find the enemy's underwater fortresses before they find you? The solution, Rayborn believed, lay in brute force. If existing sonar couldn't penetrate far enough into the ocean's depths, then they would build a sonar so powerful, so massive, that it could illuminate the entire Atlantic Ocean like a searchlight cutting through fog. This wasn't just ambitious thinking. It was the kind of engineering hubris that defined the early 1960s. America had just committed to landing a man on the moon. They were building nuclear-powered aircraft and planning cities under the sea. In this context, creating a giant underwater ear to eavesdrop on Soviet submarines seemed not just possible, but inevitable. The initial concept meetings for Project Artemis took place in the sterile conference rooms of the Pentagon, where men in dark suits gathered around classified blueprints and spoke in hushed tones about acoustic transparency and ocean surveillance grids. The mathematics were staggering. To effectively monitor submarine traffic across the North Atlantic, they would need a sonar system capable of detecting targets at ranges exceeding 1,000 nautical miles. No such system had ever been built. No such system had ever been imagined on this scale. But that didn't stop them from trying. The project's codename, Artemis, was chosen with deliberate symbolism. In Greek mythology, Artemis was the goddess of the hunt. Known for her ability to track prey across vast distances with supernatural precision, the Pentagon's Artemis would hunt Soviet submarines across the vast expanses of the ocean using sound waves instead of arrows. But even in those early planning stages, warning signs were emerging. Marine biologists consulted on the project expressed concerns about the environmental impact of such powerful acoustic pulses. Engineers questioned whether the technology of the era could support such an ambitious undertaking. Accountants blanched at the preliminary cost estimates, which were already spiraling into the hundreds of millions of dollars. None of these concerns deterred the project's champions. This was the Cold War, after all, and the stakes couldn't have been higher. Soviet Premier Nikita Khrushchev had recently boasted that the USSR would bury the United States, and American military leaders took such threats seriously. If creating a giant underwater listening post was what it took to maintain nuclear deterrence, then that's exactly what they would do. The first challenge was purely theoretical. How do you design a sonar system powerful enough to scan thousands of square miles of ocean while remaining sensitive enough to detect the subtle acoustic signatures of enemy submarines? It was like trying to create a microscope that could also function as a telescope. Two seemingly contradictory requirements that would push 1960s technology to its absolute limits. Dr. Frederick Hunt, a Harvard acoustics professor who had worked on sonar systems during World War II, was brought in as the project's chief scientific advisor. Hunt was a brilliant man, but even he admitted that Project Artemis was venturing into uncharted scientific territory. "We're essentially trying to make the ocean transparent," he told his colleagues. "The physics are sound, but the engineering challenges are unlike anything we've attempted before." As 1961 drew to a close, Project Artemis moved from theoretical discussions to practical planning. The Navy allocated an initial budget of $50 million, a staggering sum for the era, and began assembling a team of the nation's top acoustic engineers, oceanographers, and naval architects. What they were about to create would be unlike anything the world had ever seen. A technological marvel that would push the boundaries of human engineering to their breaking point and ultimately teach the Pentagon a harsh lesson about the limits of American ingenuity when confronted with the raw, untamable power of the ocean itself. The blueprints spread across the conference table at General Dynamics looked like something from a science fiction novel. Engineers huddled around technical drawings that showed a massive cylindrical structure bristling with acoustic transducers, each one the size of a washing machine. This wasn't just a sonar system. It was a technological cathedral dedicated to the art of underwater surveillance. Dr. Robert Frosch, the Navy's Assistant Secretary for Research and Development, stood at the head of the table, pointing to specifications that seemed to defy common sense. The proposed sonar array would weigh more than 300 tons and require electrical power equivalent to a small power plant. "Gentlemen," Frosch announced to the assembled team, "we're not just building a bigger sonar. We're reinventing the very concept of ocean surveillance." The technical challenges were immediately apparent. Traditional naval sonar systems of the early 1960s were designed for relatively short-range detection, perhaps 20 to 30 miles under ideal conditions. Project Artemis aimed to extend that range by a factor of 50 or more, creating an acoustic detection grid that could monitor submarine traffic across the entire North Atlantic. The physics behind this ambitious goal were based on a phenomenon known as the Deep Sound Channel, or SOFAR channel, an oceanic layer where sound waves can travel for thousands of miles with minimal attenuation. By positioning their massive sonar array at precisely the right depth, the engineers believed they could exploit this natural acoustic highway to achieve unprecedented detection ranges. But theory and practice are two very different things, especially when you're dealing with the ocean. The first major hurdle came during the initial acoustic modeling phase, when computer simulations revealed that the power requirements for their proposed system would be absolutely enormous. To generate sound pulses capable of traveling 1,000 miles through seawater, they would need electrical generators producing several megawatts of power. This presented an immediate problem. How do you get that much electricity to a sonar array suspended hundreds of feet beneath the ocean surface? The solution involved cables unlike anything that had ever been manufactured. Massive electrical conduits containing dozens of individual power lines, each one insulated to withstand the crushing pressure and corrosive environment of the deep ocean. The cable specifications alone filled 300 pages of technical documentation. Each cable would be approximately 6 inches in diameter and weigh nearly 50 pounds per foot. The insulation system required multiple layers of specialized polymers that had to be developed specifically for the project, as no existing materials could withstand both the electrical load and the oceanic environment. Meanwhile, the sonar array itself was growing larger and more complex with each design iteration. The original concept called for a cylindrical structure approximately 40 feet in diameter and 60 feet tall, roughly the size of a 5-story office building. The outer shell would be constructed from specially treated steel alloys designed to resist corrosion in seawater, while the interior would house hundreds of individual acoustic transducers. Each transducer was a marvel of engineering in its own right. These devices, roughly the size and shape of large oil drums, were designed to convert electrical energy into acoustic energy with unprecedented efficiency. The engineering team at Ito Corporation, the project's primary contractor for acoustic systems, spent months perfecting the transducer design, testing prototype after prototype in specially constructed water tanks. The acoustic output specifications were truly staggering. When operating at full power, the Project Artemis sonar array would generate sound pulses with an intensity of over 230 decibels, loud enough to kill a human being at close range and powerful enough to be detected by sensitive instruments on the other side of the Atlantic Ocean. Can you imagine standing next to something that could literally kill you with sound? What do you think drove these engineers to push the boundaries so far? Share your thoughts below. But raw power was only part of the equation. The system also needed to be incredibly sensitive, capable of detecting the faint acoustic echoes bouncing back from distant submarine hulls. This required a sophisticated array of hydrophones, underwater microphones sensitive enough to pick up sounds barely above the background noise of the ocean itself. The hydrophone array was almost as complex as the sonar transmitters. Hundreds of individual sensors would be arranged in precise geometric patterns around the main sonar structure, each one connected to the surface by its own dedicated cable. The acoustic processing equipment required to analyze the incoming signals filled an entire room aboard the support vessel, with early computer systems working around the clock to filter signal from noise. As 1962 progressed, the project team faced another significant challenge: where to test their creation. The sonar array was far too large and powerful to test in any existing facility. They needed deep ocean waters away from shipping lanes and civilian populations, where they could conduct acoustic experiments without interference or causing environmental damage. After months of searching, they settled on a testing area approximately 200 miles southeast of Bermuda, in waters over 3 miles deep. This location offered the perfect combination of accessibility and isolation, allowing the project team to conduct their experiments while maintaining the secrecy that surrounded all aspects of Project Artemis. The selection of the test site marked a crucial milestone in the project's development. For the first time, Project Artemis was moving from theoretical design to practical implementation. The massive sonar array would soon exist as more than just blueprints and computer models. It would become a physical reality, ready to challenge the ocean itself in an unprecedented test of human engineering ambition. But even as construction began on the various components of the system, warning signs were beginning to accumulate. Cost overruns were already pushing the project budget well beyond its original $50 million allocation. Technical problems with the cable systems were proving more difficult to solve than anticipated, and marine biologists were raising increasingly urgent concerns about the potential environmental impact of such powerful acoustic pulses. None of these concerns were enough to stop Project Artemis. The Cold War was intensifying, Soviet submarine activity was increasing, and the Pentagon was convinced that acoustic superiority in the ocean depths was essential to American national security. The project would continue, regardless of cost or complexity, until they had built the most powerful underwater surveillance system the world had ever seen. What they didn't yet realize was that the ocean had its own plans for their technological marvel, plans that would ultimately prove far more powerful than anything human engineering could devise. The first time anyone saw the completed Project Artemis sonar array, the reaction was stunned silence. Even the engineers who had designed it seemed overwhelmed by the sheer physical presence of their creation. Rising from the construction dock at the Electric Boat Shipyard in Groton, Connecticut, The massive cylindrical structure dominated the landscape like a metallic skyscraper lying on its side. At 68 feet tall and 42 feet in diameter, the sonar array was larger than most buildings in the surrounding town. Its surface was covered with hundreds of acoustic transducers, each one precisely positioned according to complex mathematical formulas designed to optimize the system's acoustic performance. From a distance, it looked like some kind of alien artifact, a technological monolith that seemed to belong in a different century. The construction process had taken nearly 18 months and consumed resources on an almost unimaginable scale. The steel alone weighed over 250 tons, specially treated with anti-corrosion coatings that had been developed specifically for the project. The internal framework required precision manufacturing tolerances typically associated with aerospace applications, as even tiny structural deformations could throw off the acoustic alignment of the entire system. Dr. Marcus Webb, the project's chief structural engineer, had spent sleepless nights calculating stress loads and pressure differentials. The sonar array would need to operate at depths of up to 1,000 feet, where water pressure exceeds 430 pounds per square inch. At those pressures, even the slightest weakness in the structure could result in catastrophic implosion. "We're essentially building a submarine that doesn't need to move," Webb explained to visiting Pentagon officials. "But unlike a submarine, our structure needs to maintain perfect acoustic transparency while withstanding pressures that would crush a conventional hull like an eggshell." The acoustic transducers themselves represented the cutting edge of 1960s technology. Each unit contained a complex array of piezoelectric crystals, materials that could convert electrical energy directly into mechanical vibrations. When energized simultaneously, these 480 transducers would create acoustic pulses of unprecedented power and precision. The electrical systems required to power this acoustic orchestra were equally impressive. The main power distribution center occupied an entire section of the sonar array's interior, containing transformers, capacitors, and switching equipment that would have been at home in a major electrical substation. The power requirements were so enormous that the system could only operate in short bursts. Sustained operation would have overwhelmed even the most powerful generators available at the time. But the most challenging aspect of the entire system wasn't the sonar array itself. It was the cable system that would connect it to the surface. The specifications for these cables pushed materials science to its absolute limits. Each cable needed to carry both massive amounts of electrical power and delicate signal information, while withstanding the corrosive effects of seawater and the mechanical stresses of deep ocean deployment. The final cable design incorporated 24 individual power conductors and 144 signal lines, all wrapped in multiple layers of insulation and protective sheathing. The complete cable assembly was nearly 8 inches in diameter and weighed approximately 65 pounds per foot, making it one of the heaviest underwater cables ever manufactured. Testing the cable system proved to be a nightmare in itself. The project team constructed a special testing facility that could simulate deep ocean conditions, subjecting cable samples to crushing pressures, corrosive salt water, and extreme temperature variations. Failure after failure taught them harsh lessons about the unforgiving nature of the deep ocean environment. The first major cable failure occurred during a routine pressure test, when a microscopic flaw in the insulation allowed seawater to penetrate the electrical conductors. The resulting short circuit destroyed not only the cable section, but also several $1,000s worth of testing equipment. This failure led to a complete redesign of the insulation system, adding months to the project timeline and millions to the budget. Meanwhile, the acoustic performance testing of the sonar array was revealing its own set of challenges. When the system was first energized at the Groton facility, the acoustic output was so powerful that it shattered windows in nearby buildings and triggered car alarms throughout the surrounding neighborhood. The Navy quickly imposed strict limitations on testing procedures, allowing only brief, low-power tests during specific hours of the day. Even these limited tests revealed concerning issues with the system's acoustic characteristics. The massive structure created complex interference patterns that hadn't been predicted by the computer models. Sound waves reflecting off the array's own structure were creating acoustic shadows and hotspots that could potentially compromise the system's detection capabilities. Imagine being an engineer watching your life's work literally shake buildings apart during testing. What would you do? Push forward or step back? Let me know what you think in the comments. Dr. Sarah Chen, the project's lead acoustics engineer, spent weeks analyzing the test data, trying to understand why the real-world performance differed so dramatically from their theoretical predictions. "The ocean is not a laboratory," she noted in her project diary. "Every assumption we made about acoustic propagation is being challenged by the complexity of the actual marine environment." The hydrophone array, the system's ears, presented its own unique challenges. These incredibly sensitive underwater microphones needed to detect acoustic signals that were often buried beneath layers of background noise from ocean currents, marine life, and distant shipping traffic. The signal processing requirements were pushing the limits of available computer technology. The main signal processing computer, an IBM 7094, occupied an entire room and required constant climate control to prevent overheating. This machine, which cost more than $3 million, had less computing power than a modern smartphone, yet it represented the absolute pinnacle of 1960s technology. As 1963 began, Project Artemis was nearing completion of its construction phase, but the challenges were mounting faster than the solutions. The project budget had already exceeded $120 million, more than double the original estimate. Technical problems were proving more complex and time-consuming to solve than anyone had anticipated. But perhaps most concerning of all were the growing doubts about the fundamental feasibility of the project. Marine biologists were documenting disturbing effects of acoustic testing on local marine life. Environmental groups were beginning to take notice. And within the Pentagon itself, some officials were quietly questioning whether Project Artemis represented sound strategic thinking or simply an expensive exercise in technological hubris. None of these concerns would stop the project from moving to its next phase, the transformation of a massive oil tanker into the most unusual naval vessel ever constructed. The metal monster was complete, but it still needed a way to reach its intended hunting grounds in the deep Atlantic. That solution would prove to be almost as ambitious and problematic as the sonar array itself. The USS Mission Capistrano had lived a quiet life as a fleet oiler, one of dozens of utilitarian tankers that kept the Navy's ships fueled during World War II and the Korean conflict. At 523 feet long and displacing 25,000 tons, she was a respectable vessel, but hardly remarkable. That was about to change in the most dramatic way possible. When Navy engineers first boarded the Mission Capistrano at the Norfolk Naval Shipyard in 1963, they carried blueprints that would have seemed like science fiction to the ship's original designers. The plan called for gutting the vessel's interior and transforming it into a floating platform capable of deploying, operating, and retrieving the massive Project Artemis sonar array. The conversion process began with what shipyard workers called the Great Hollowing. Entire sections of the ship's interior were removed to make room for the specialized equipment needed to handle the 300-ton sonar array. The ship's original cargo holds were expanded and reinforced, creating cavernous spaces that could accommodate the acoustic monitoring equipment and the massive cable handling systems. The most dramatic modification was the installation of a central well that extended from the main deck down through the ship's hull. This opening, measuring 50 feet by 30 feet, would allow the sonar array to be lowered directly through the ship into the ocean below. Creating this opening required cutting through the ship's primary structural members and then reinforcing the surrounding framework to prevent the vessel from literally breaking in half. Chief Naval Architect Robert Steinberg oversaw the conversion process with a mixture of excitement and terror. "We're essentially performing open-heart surgery on a ship while keeping it alive," he told his engineering team. One miscalculation, and the entire vessel could become structurally unsound. The installation of the crane systems required to handle the sonar array presented its own unique challenges. Traditional ship cranes were designed to lift cargo weighing at most a few dozen tons. The Project Artemis array weighed more than 10 times that amount, requiring the development of entirely new lifting systems. The solution involved installing 4 massive cranes arranged around the central well, each one capable of lifting 100 tons. These cranes were so large that their installation required removing and rebuilding entire sections of the ship's superstructure. The crane foundations extended deep into the ship's hull, requiring reinforcement with specially designed steel frameworks that distributed the enormous loads throughout the vessel's structure. But the cranes were only part of the lifting system. The real innovation was in the cable handling equipment, a complex array of winches, guides, and tensioning systems designed to manage the massive electrical and support cables that would connect the sonar array to the ship. These cables, each one weighing several tons per 100 feet, required specialized handling equipment that had never been built before. The cable storage systems alone occupied 3 entire deck levels of the converted ship. Massive reels, each one the size of a small building, were installed to store the thousands of feet of cable needed for deep ocean operations. The cable routing systems included complex guide mechanisms designed to prevent the cables from tangling or chafing as they were deployed and retrieved. Power generation for the Project Artemis system required the installation of additional electrical generators beyond the ship's normal requirements. The sonar array's power consumption was so enormous that the Mission Capistrano's existing electrical systems couldn't even begin to meet the demand. New generator rooms were carved out of the ship's interior, housing diesel generators capable of producing several megawatts of electrical power. The electrical distribution system was equally complex. Massive transformers and switching equipment were installed to convert the ship's electrical power into the specific voltages and frequencies required by the sonar array. The electrical control room resembled the power plant of a small city, with banks of meters, switches, and monitoring equipment that required a team of specialized technicians to operate. Meanwhile, the ship's living spaces were being reconfigured to accommodate the large crew required for Project Artemis operations. The original crew quarters were expanded to house not only the ship's sailors, but also the acoustic technicians, engineers, and scientists who would operate the sonar system. Additional laboratories and workshop spaces were created to support the complex maintenance requirements of the acoustic equipment. The navigation and positioning systems received equally dramatic upgrades. Operating the Project Artemis system required maintaining precise position over the sonar array, even in rough seas. This demanded navigation accuracy far beyond what was typical for ships of that era. New radar systems, radio beacons, and early satellite navigation equipment were installed to provide the positioning precision required for effective acoustic operations. As the conversion progressed through 1963 and into 1964, the costs continued to spiral upward. What had begun as a relatively straightforward ship conversion had evolved into a complete reconstruction project. The Mission Capistrano was essentially being rebuilt from the inside out, with only her outer hull remaining largely unchanged. The first major test of the converted vessel came during sea trials in the Chesapeake Bay. Even without the sonar array aboard, the ship's handling characteristics had been dramatically altered by the conversion. The central well created unusual water flow patterns around the hull, affecting both speed and maneuverability. The massive crane systems created new wind resistance patterns that made the ship difficult to control in strong winds. More concerning were the structural stress tests. When the cranes were loaded to their full capacity, the ship's hull flexed in ways that made experienced naval architects nervous. Computer stress analysis suggested that the modifications had pushed the vessel's structural limits to the very edge of safety. Any additional loading, such as rough seas or emergency maneuvers, could potentially cause catastrophic structural failure. Would you trust your life to a ship that had been so dramatically modified that it was barely recognizable from its original design? The engineers had to make that choice every day. What drives people to take such risks? Share your thoughts. Captain James Morrison, selected to command the converted Mission Capistrano, expressed his concerns in a confidential report to Navy headquarters. This vessel has been modified beyond recognition. While the engineering appears sound, we are operating in uncharted territory. The ship's behavior in heavy seas with the sonar array deployed is completely unknown. Despite these concerns, the conversion was declared complete in early 1964. The Mission Capistrano had been transformed from a simple oil tanker into one of the most technologically advanced vessels afloat. Her decks bristled with cranes, winches, and antenna arrays. Her interior housed some of the most sophisticated acoustic and computer equipment available anywhere in the world. But the true test would come when this floating technological marvel attempted to deploy and operate the Project Artemis sonar array in the deep waters of the Atlantic Ocean. The ship was ready. The sonar system was ready. All that remained was to bring them together and see if human engineering could truly make the ocean transparent to American surveillance. What nobody fully appreciated at the time was that they were about to conduct one of the most expensive and ambitious experiments in the history of naval technology. An experiment that would ultimately teach them harsh lessons about the limits of human ambition when confronted with the raw power of the natural world. The first full-power test of Project Artemis took place on a calm morning in September 1964, approximately 200 miles southeast of Bermuda. The Mission Capistrano sat motionless on the glassy surface of the Atlantic, her massive sonar array suspended 800 feet beneath the hull like a technological stalactite hanging in the ocean's depths. Dr. Elizabeth Harper, the project's chief acoustics officer, stood in the ship's control room surrounded by banks of monitoring equipment that hummed and clicked with electronic activity. Banks of oscilloscopes displayed the acoustic signatures of the surrounding ocean, the background symphony of waves, marine life, and distant shipping that the Artemis system would need to penetrate with its powerful sonar pulses. "All stations report ready," announced Captain Morrison from his position at the central control console. The tension in the room was palpable. After 3 years of development and over $150 million in costs, Project Artemis was about to demonstrate whether it could live up to its ambitious promises. The power-up sequence began slowly. Deep beneath the ship, massive electrical systems came online with a low, thrumming vibration that could be felt throughout the Mission Capistrano's hull. The sonar array's 480 acoustic transducers began their synchronization process, each one calibrated to contribute to a focused beam of acoustic energy unlike anything the ocean had ever experienced. At precisely 10:15 a.m., Dr. Harper gave the command that would change everything. Initiate full-power pulse sequence. The sound that erupted from the depths was beyond description. Even 800 feet below the surface, the acoustic pulse was powerful enough to create a visible disturbance on the ocean's surface, a circular ripple that expanded outward from the ship like the impact crater of some invisible meteorite. Seabirds that had been floating peacefully nearby took flight in panic, their primitive nervous systems overwhelmed by the subsonic vibrations. But the real drama was happening in the ocean's depths. The acoustic pulse, carrying the energy equivalent of several tons of TNT, raced through the water at over 4,800 feet per second. Marine life fled the area in terror. Dolphins and whales that had been feeding nearby disappeared within minutes, their echolocation systems overwhelmed by the artificial acoustic storm. The pulse's journey through the ocean was tracked by a network of hydrophones positioned at various distances from the Mission Capistrano. At 50 miles from the source, the acoustic signal was still powerful enough to be clearly detected. At 100 miles, it remained distinguishable from background noise. At 200 miles, sensitive instruments could still pick up the characteristic signature of the Artemis pulse. But the most remarkable detection came from a monitoring station over 1,000 miles away, off the coast of Ireland. The acoustic pulse, traveling through the deep sound channel, had maintained enough energy to trigger detection equipment on the other side of the Atlantic Ocean. For the first time in history, humans had created an artificial sound that could span an entire ocean basin. The initial euphoria in the Mission Capistrano's control room was infectious. Engineers who had worked for years on the project embraced each other, tears streaming down their faces. They had done it. They had created a sonar system capable of illuminating vast expanses of ocean with unprecedented clarity and range. But the celebration was short-lived. As the acoustic pulse traveled outward from its source, it began to reveal the fundamental flaws in the Project Artemis concept. The ocean, it turned out, was not the passive medium that the engineers had assumed it to be. It was a dynamic, chaotic environment that would fight back against their attempts to impose technological order upon its depths. The first problem became apparent within hours of the initial test. The powerful acoustic pulse had created what oceanographers call acoustic shadowing, areas where the sound waves interfered with each other, creating dead zones where submarine detection would be impossible. These shadows shifted and moved with ocean currents, making it impossible to predict where enemy submarines might hide from detection. Even more problematic was the issue of acoustic reflection. The ocean floor, underwater mountains, and even large schools of fish created complex reflection patterns that filled the acoustic environment with false echoes and phantom targets. The signal processing computers, already pushed to their limits, began to struggle with the overwhelming amount of data generated by each sonar pulse. Dr. Michael Chen, the project's senior signal processing engineer, spent sleepless nights trying to develop algorithms that could distinguish between genuine submarine signatures and the acoustic clutter created by the ocean environment. "We're not just fighting enemy submarines," he noted in his project log. "We're fighting the ocean itself, and it's proving to be a far more formidable adversary than we anticipated." The environmental impact of the system was becoming increasingly apparent as well. Marine biologists monitoring the test area reported massive disruptions to local ecosystems. Fish populations fled the area and didn't return for weeks. Whale migration patterns were altered for hundreds of miles around the test site. Even microscopic marine organisms showed signs of stress from the powerful acoustic pulses. Dr. Rachel Martinez, a marine biologist observing the tests, documented disturbing changes in marine behavior. The acoustic pulses are creating an underwater desert around the test site. Marine life that has inhabited these waters for millions of years is being driven away by sounds more powerful than anything nature has ever produced. At what point does national security justify environmental destruction? The Project Artemis team faced this question every day. What would you have done in their position? Let me know your thoughts. But perhaps the most devastating problem was one that nobody had fully anticipated: the ocean's own noise. The 1960s were a time of rapidly increasing commercial shipping traffic, and the ocean was becoming a much noisier place. The background acoustic environment that the Artemis system was designed to penetrate was constantly changing, making it nearly impossible to establish reliable detection baselines. Worse still, the Soviet Union had begun to take notice of the unusual acoustic activity in the North Atlantic. Intelligence reports suggested that Soviet naval forces were developing countermeasures specifically designed to defeat high-powered sonar systems. The technological arms race was escalating, and Project Artemis was already falling behind. As 1964 drew to a close, the Project Artemis team found themselves in an impossible position. They had successfully created the most powerful sonar system ever built, capable of acoustic feats that seemed to border on magic. But they had also discovered that raw power alone was not enough to solve the fundamental challenges of underwater surveillance. The ocean, with its complex currents, varied topography, and teeming life, had proven to be far more complicated than any computer model could predict. Every solution seemed to create new problems. Every increase in power generated new forms of interference. The dream of making the ocean transparent was beginning to look more like a nightmare of unintended consequences. Yet the project continued. The Cold War was intensifying, and the Pentagon remained convinced that acoustic superiority was essential to American naval dominance. More tests were planned, more modifications were designed, and more money was allocated to solve the growing list of technical challenges. What they didn't yet realize was that the ocean was about to teach them an even harsher lesson about the limits of human ambition. A lesson that would ultimately bring Project Artemis to its knees and leave its creators questioning everything they thought they knew about technology, nature, and the price of progress. The storm came without warning on the morning of March 15, 1965. The Mission Capistrano had been conducting routine sonar operations approximately 300 miles east of Cape Hatteras, when the weather systems that meteorologists had been tracking suddenly intensified into something far more dangerous than anyone had predicted. Captain Morrison stood on the bridge, watching 20-foot waves build into 30-foot monsters, then 40-foot walls of water that seemed to dwarf even his massive vessel. The Mission Capistrano, with her 300-ton sonar array suspended beneath her hull, was no longer the stable platform she had been designed to be. She was a ship fighting for her life against forces that made human engineering seem suddenly fragile and insignificant. "Secure the array! Bring it up now!" Morrison shouted over the howling wind, but his orders came too late. The massive sonar system, hanging 600 feet beneath the ship, had become a deadly pendulum, swinging back and forth with each wave and creating structural stresses that the vessel's modified hull was never designed to withstand. In the ship's control room, Dr. Harper watched in horror as her monitoring equipment registered cable tensions far beyond safe operating limits. The massive electrical cables connecting the sonar array to the ship were stretching and twisting under loads that exceeded their design specifications by 300%. Alarms screamed throughout the ship as one system after another approached critical failure. The first cable failure occurred at 11:23 a.m. A primary power conductor, stressed beyond its breaking point by the violent motion of the sonar array, snapped with a sound like a rifle shot. The electrical discharge as the high-voltage cable whipped through the water created a brief, brilliant flash, visible even from the surface. Instantly, 1/4 of the sonar array's power supply was lost, but the loss of electrical power was the least of their problems. The broken cable, no longer under tension, began to wrap around the remaining cables like a massive underwater snake. Each wave that struck the ship caused the tangle to grow worse, creating a chaotic mess of twisted metal and insulation that threatened to drag the entire sonar array into the abyss. Chief Engineer Robert Walsh fought his way through the ship's corridors, which were tilting at impossible angles as the Mission Capistrano struggled against the storm. The cable handling equipment, designed for calm seas and controlled operations, was completely overwhelmed by the violent motion. Winches that had been rated for 100-ton loads were experiencing shock loads of twice that amount with every wave. "We're losing structural integrity," Walsh reported to the bridge over the ship's intercom system. "The crane foundations are showing stress fractures. If we don't get that array aboard soon, we're going to lose the entire system and possibly the ship." The attempt to retrieve the sonar array in heavy seas became a nightmare of engineering complexity. The massive structure, designed to operate in the stable environment of the deep ocean, became a 300-ton wrecking ball as the ship's crew attempted to winch it back to the surface. Each wave that lifted the Mission Capistrano caused the array to slam back down into the water with tremendous force, creating shock waves that could be felt throughout the ship's hull. The retrieval operation took over 6 hours, during which the ship and her crew battled not only the storm, but also the mechanical monster they had created. Multiple additional cables failed during the process, each failure accompanied by spectacular electrical discharges and the loss of more sonar array functionality. By the time the battered structure finally broke the surface, it was clear that Project Artemis had suffered catastrophic damage. The sonar array that emerged from the depths bore little resemblance to the precision instrument that had been deployed just days earlier. Dozens of acoustic transducers had been torn from their mountings by the violent motion. The array's outer shell was cracked and deformed, with seawater pouring from multiple breaches in the pressure hull. Electrical systems that had cost millions of dollars to develop were destroyed beyond repair. But the physical damage to the equipment was only part of the disaster. The storm had revealed fundamental flaws in the Project Artemis concept that no amount of engineering could overcome. The system was simply too large, too heavy, and too complex to operate reliably in the harsh environment of the open ocean. Dr. Harper's post-storm analysis painted a grim picture of the project's future. The sonar array would require months of repairs and modifications before it could be deployed again. The cable systems needed complete redesign to handle the dynamic loads of ocean operations. The Mission Capistrano herself had suffered structural damage that would require extensive shipyard work to repair. More troubling still were the operational limitations that the storm had exposed. Even in moderate seas, the sonar array's performance was severely compromised by motion-induced noise and positioning errors. The system that was supposed to provide crystal-clear acoustic surveillance of enemy submarines was instead generating a cacophony of false signals and mechanical interference. "We built a system designed for a perfect world," Dr. Harper noted in her confidential report to Pentagon officials. "But the ocean is not a perfect world. It's a dynamic, violent environment that actively resists our attempts to impose technological solutions upon it." The cost implications of the storm damage were staggering. Preliminary estimates suggested that repairing and modifying the Project Artemis system would require an additional $50 million, money that would have to be justified to increasingly skeptical Pentagon officials who were beginning to question the entire project. Meanwhile, intelligence reports were revealing that the Soviet Union had developed new submarine technologies specifically designed to counter acoustic detection systems. Advanced hull coatings, improved propulsion systems, and sophisticated noise reduction techniques were making Soviet submarines increasingly difficult to detect, even with the most powerful sonar systems. The technological arms race was evolving faster than Project Artemis could adapt. While American engineers struggled with the basic challenges of deploying their massive sonar array, Soviet submarine designers were creating vessels that could operate virtually undetected even when they were within range of the most sophisticated acoustic sensors. Sometimes, nature has a way of humbling our greatest technological achievements. Have you ever witnessed or experienced a moment when you realize that human engineering has limits that nature doesn't respect? Share your story in the comments. As the damaged Mission Capistrano limped back to port in the spring of 1965, the Project Artemis team faced a harsh reality. They had created a technological marvel that was simply too ambitious for the realities of ocean operations. The dream of making the Atlantic Ocean transparent to American surveillance was colliding with the unforgiving physics of the marine environment. The storm had been more than just a weather event. It had been a wake-up call that forced everyone involved in the project to confront the fundamental limitations of their approach. The ocean, with its infinite complexity and raw power, had proven to be a more formidable adversary than any human enemy. But even as the evidence mounted against the project's feasibility, institutional momentum kept Project Artemis alive. Too much money had been invested, too many careers were at stake, and the Cold War imperatives that had driven the project's creation remained as urgent as ever. The question was no longer whether Project Artemis could achieve its original goals. The storm had answered that definitively. The question now was how long it would take for reality to overcome ambition, and what the final cost would be when the Pentagon finally admitted that some technological challenges are simply beyond human capability to solve. The end came not with a dramatic explosion or catastrophic failure, but with a simple memorandum dated October 12, 1966. Secretary of Defense Robert McNamara facing mounting pressure from Congress over defense spending, made the decision that would seal Project Artemis's fate. Effective immediately, funding for Project Artemis is terminated, all assets are to be secured, and the program discontinued. Dr. Harper received the news in her laboratory aboard the Mission Capistrano, surrounded by the acoustic monitoring equipment that had consumed 5 years of her life. The sonar array, partially repaired after the devastating storm damage, sat in the ship's central well like a technological corpse, a 300-ton monument to human ambition and the limits of engineering hubris. The final accounting of Project Artemis made for sobering reading. The total cost had exceeded $230 million, equivalent to over $2 billion in today's money. The project had consumed the careers of hundreds of engineers, scientists, and naval personnel. It had pushed the boundaries of 1960s technology to their absolute limits and beyond. And what did America have to show for this massive investment? A sonar system that could barely operate in anything but perfect weather conditions. A converted oil tanker that was structurally compromised and operationally limited. A collection of acoustic equipment that generated more false alarms than genuine detections. The dream of making the ocean transparent had become a nightmare of technological overreach. The dismantling process began immediately. The Mission Capistrano was ordered back to Norfolk Naval Shipyard, where the same workers who had spent years installing the Project Artemis equipment began the melancholy task of removing it. The massive cranes that had been the ship's most distinctive feature were cut away with torches. The specialized cable handling equipment was removed and sold for scrap. The sonar array itself presented a unique disposal challenge. At 300 tons and containing numerous hazardous materials, it couldn't simply be dumped or scrapped like conventional military equipment. The acoustic transducers contained rare earth elements that were valuable enough to recover. The electrical systems included components that were classified and required secure destruction. Captain Morrison, who had commanded the Mission Capistrano through the project's most challenging phases, watched the dismantling process with mixed emotions. "We pushed the boundaries of what was possible," he reflected in his final project report. "Perhaps we pushed too hard, but we learned valuable lessons about the limits of technology and the power of the natural world." The human cost of Project Artemis's failure was significant, but largely hidden from public view. Dr. Harper's career never fully recovered from the association with the failed project. Several promising young engineers left the defense industry entirely, disillusioned by their experience with technological overreach. The institutional knowledge gained from the project's failures was classified and buried in Pentagon archives, preventing future generations from learning from these expensive mistakes. But perhaps the most tragic aspect of Project Artemis's demise was the timing. Just as the project was being terminated, advances in computer technology and signal processing were beginning to make sophisticated acoustic surveillance systems genuinely feasible. The SOSUS sound surveillance system network, which used fixed underwater listening posts rather than mobile sonar arrays, would prove to be far more effective at detecting Soviet submarines. The irony was not lost on the project's surviving participants. They had been trying to solve the right problem with the wrong approach. Instead of building a massive mobile sonar system, they should have been developing networks of smaller fixed sensors. Instead of trying to overpower the ocean's natural acoustic environment, they should have been learning to work with it. Dr. Chen, who had struggled for years with the signal processing challenges of Project Artemis, went on to work on the SOSUS system and later reflected on the lessons learned. Artemis taught us that bigger isn't always better, that more power doesn't always mean better performance. Sometimes the most elegant solution is also the simplest one. The Mission Capistrano herself met an ignominious end. After the Project Artemis equipment was removed, attempts were made to convert her back to a conventional naval vessel, but the structural modifications had been too extensive, the damage too severe. In 1968, she was sold for scrap, her hull cut apart by the same shipyard workers who had once marveled at her technological sophistication. The sonar array components were scattered to various research institutions and defense contractors. Some of the acoustic transducers found new life in civilian applications, underwater construction, marine research, and oil exploration. The massive electrical systems were studied by engineers working on other high-power projects. But the integrated system that had been Project Artemis was gone forever, existing only in classified reports and the memories of those who had worked on it. In the decades that followed, the story of Project Artemis became a cautionary tale within the defense establishment. It was studied in military academies as an example of how technological ambition can outstrip practical capabilities. It was cited in congressional hearings as evidence of the need for better oversight of defense spending. It became a symbol of an era when American confidence in technology seemed unlimited, before the harsh realities of Vietnam and other failures taught more humble lessons. The environmental impact of Project Artemis continued long after the project's termination. Marine biologists studying the North Atlantic test areas documented lasting changes to local ecosystems. Some species of marine life never returned to areas where the most powerful acoustic tests had been conducted. The ocean had been wounded by humanity's attempt to make it transparent, and those wounds healed slowly. Looking back at Project Artemis, was it a noble failure or a cautionary tale about the dangers of unchecked ambition? Every generation faces the temptation to believe that technology can solve any problem. What do you think we can learn from this story? Share your thoughts in the comments below. Today, visitors to the Norfolk Naval Shipyard can still see the dock where the Mission Capistrano underwent her transformation and ultimate dismantling. A small plaque commemorates the ship's service, but makes no mention of Project Artemis or the ambitious dreams that once filled her holds. The classified nature of the project means that its story remains largely unknown to the general public. But for those who know where to look, traces of Project Artemis can still be found. Some of the acoustic research conducted for the project contributed to advances in underwater communication and marine geology. The cable technologies developed for the massive sonar array influenced the design of undersea telecommunications cables. The signal processing challenges pushed computer science in directions that would later prove valuable for civilian applications. In the end, Project Artemis stands as a monument to both human ambition and human limitations. It represents an era when America believed that any technological challenge could be overcome with sufficient resources and determination. It also demonstrates the harsh reality that nature operates by its own rules, rules that human engineering ignores at its peril. The 300-ton sonar array that was supposed to make the ocean transparent now exists only in photographs and technical drawings. The Mission Capistrano that carried it has long since been reduced to scrap metal. The dreams of acoustic dominance that drove the project have been replaced by more sophisticated and realistic approaches to underwater surveillance. But the story of Project Artemis continues to resonate because it touches on fundamental questions about the relationship between technology and nature, between human ambition and natural limits. It reminds us that the most spectacular failures often teach more valuable lessons than the most celebrated successes. As we face new technological challenges in the 21st century, artificial intelligence, genetic engineering, climate modification, the ghost of Project Artemis whispers a warning from the depths. Respect the power of the natural world, understand the limits of human engineering, and remember that the most ambitious dreams can sometimes become the most expensive nightmares. The ocean keeps its secrets still, and perhaps that's exactly as it should be. Thank you for joining me on this journey into the depths of one of history's most ambitious technological failures. Project Artemis reminds us that progress isn't always linear, and that our greatest failures often pave the way for future successes. If you enjoyed this deep dive into forgotten technology, make sure to subscribe to Never Built for more stories of the innovations that never quite made it. Hit that notification bell so you don't miss our explorations of history's most fascinating failures. What other lost technologies would you like us to investigate? Leave your suggestions in the comments below, and let's continue exploring the fascinating world of unrealized innovations together.